So shall we start or give people some more time?
I think we're good to go. I think, yeah, there's quite a few people here now, so I think it's a few minutes after the hour as well, so we can get going.
Okay, so I'll start now. So good morning and evening for some of you, everyone. So today I will give tutorial on understanding the simulation output. So this is meant to be an intermediate level tutorial for those who probably have had a few experience on working with epic simulations and started to wonder where those variables are generated. So in terms of the exercise and the practice, we will do everything on Jupyter Notebook, and that will be hosted through the Google Colab. So technically, you just need a browser and a Google account for this session. There are other tutorials which will walk you through the setup of the standard EIC software environment, which you can find here. But for today, we really just need to start with some minimum requirement. And for those of you who prefer to do your analysis or open root files in C++ instead of Python, there is another nice tutorial in how you can do analysis with standard root script. Okay, so with that, we hope.
हाँ जो बीच में हुई थी ना
Hello? Was there a question?
I think it was me, someone unmuted accidentally. It's okay.
Okay, never mind. So I prepared 2 hours of materials, but we can always have more time for questions. Let's start from the first part, which is set up your Jupyter Notebook environment. So I wish everybody in this meeting have access to this page. And then what you need to do is just click this link here. Oops. Okay, open a new tab. Yeah, that's what I'm supposed to do. Here, so you have this Jupyter Notebook, and this you will need to sign into your own Google account to be able to make changes and make copies. So to do that, you just need to save this copy to your own Google Drive. And Stephen, I will need to, if you can pause a little bit here. Thank you. Okay, here, so you can see there is an option to save a copy in Drive. And that will bring you to a copy under your own Google account where you should have the all the permissions to modify or execute the cells. So today we'll be using mainly 2 packages to interact with the root files. The first one is uproot, which many of you might have heard about, and this is, I would say, a very popular way of how people use root with Python. And we also use this xrootd, which is basically a package, allow you to access root files in the remote server. And I would ask you now to run the first cell, just to click this triangle button. And this will take about 10 minutes. And the part is because we are running it in Google Colab, so I have to reinstall CMake because of some conflicts between CMake version and the Xroot version. So if you prefer to do it in your own Jupyter Notebook environment, you don't need to run this step. You just need to make sure that you have all the packages installed. That is Xroot and Uproot. And here you see I'm also install a package called Particle. This is actually how you can get access to the PDG ID and the other particle informations. It's a very convenient package to use. I will show you later. And I hope now everybody started running the cell because it takes about 10 minutes. I wish we can start and stop at the almost the same time. All right. If no further question now, I will just go back to our tutorial page and move to the next section while we just letting the code running on the background. Okay, so understanding the simulation output, what I mean by simulation is actually two parts. So we have the simulation output directly from the Gen4-based DD4HAP simulation. And then we use this simulated heads as input to do reconstruction. And we have the reconstruction output, which is also root files. So today I will go through both the inputs of outputs of both process. So this section, we will be focusing on the DD4HAP simulation package. As I mentioned earlier, so this is Gen4-based simulation package. So basically it takes particles as input and it will propagate your particles through magnetic field and materials. And your incoming or outgoing particles information, as well as all the detector signals as generated during the Gen4-based simulation are saved in the output root files. So, by the way, I hope the font size is large enough for everyone here. Let me actually make it slightly larger. How about this? Probably better. Okay, so let's go through some of the inputs. The first one is that it takes particles, which you can often produce by using some dedicated event generator, for example, PCR8, if you know what physics channels you wanted to investigate. And those event generators, their input will be, their output will be provided to DD4HAP as this HAP-MC format. Here I'm linking you to a paper on HAP-MC format where you can find all the details, but I'm not going to describe all the variables today. And the other way to generate initial particles will be using the DD4HAP's particle gun. Basically, that means you do not, if you know you just wanted to generate, for example, a uniform distribution in momentum and angle and single particles, you can just use this particle gun as a command line option when you run the DD4HAP simulation. And there is already a nice tutorial on how you can do it with DDSim, which is a command DD4HAP used to run the simulations. And then the second piece of the input that a DD4HAP needs is a detector description. We have our EPIC detector description in DD4HAP compatible format, which is maintained on GitHub. So I will walk you through the directory repository later. And here I just wanted to point you to some of the formatting related information. And actually, so let's just click on this link with a new tab. Okay, so this brings you to this page, EIC/Epic, where you can find all our detector geometry description. And if I scroll down here, you can see actually we have a 2D view of our detectors. If you are not yet familiar with this detector system, I would suggest you to take a look at this 2D view, as well as some of those viewers it provided. This, for example, if you click on this link, it will open a 3D viewer of the detector, which I find is quite helpful. And okay, so probably one more word here. Today, let me zoom in a little bit. So today we will be, most of the time you will see me talking about part of the tracking detectors, because that is the part I'm more familiar with, and I will use it as an examples later. And for example, our when I say vertex barrels, it means those three very thin layers of detector barrels in the center of the detector. And you will see this you will see the hits and the positions related to this detector later in the tutorial. Okay, and let's come back. What is relevant now is if you go to this compact folder and then go to tracking. So here you see all those XML files. Each of them contains a sub-detector description of the tracking system. And if you now just open this one, Vertex Barrel, you can see that it comes with very nice user-friendly format that you can just scroll over. But what I wanted to show you today is actually this part on the bottom. It's a readouts module. And you can see here on the readouts, you define the name of the readout. So vertex barrel hits, that is the branch name that you will see later in our DD4HAP simulation output. And the next line, you have this segmentation. And in this case, this is a 2D grid in X and Y with a size of 20 micron, which is an approximation of our silicon pixel size. So segmentation basically is a DD4HAP way to create a mesh grid. And this is how we simulate the spatial resolution of the detector that we will use later when we need to digitize the hit. And also you will see here, you define something called ID, which is 64 bits unique number for each of the those segmentation cell that we defined. And so there are 64 bits in total. You will have actually it's from right to left. So those 32 bits give you the X, Y, and Y indices of this segmentation grid you just created. And the other parts of those ID give you information like what detector system it is and what layer it is. Okay, with that, let's go back to our tutorial. And this is the time we can look at the output, and hopefully we will have our installation here finalized. Okay, so it is done on my end. And can everybody confirm that you have completed this cell? So please raise your hand or just speak out if you have questions or you see an error message on your end. Okay, I didn't notice anything, so one raised hand. Yes?
Hi, probably it's not a question here, but the one that you just explained about the cell ID thing, I see
Mhm.
that the system 8 and layer 4, does it mean it's like an increment of this thing, or is the layer 4 a fixed number?
Oh, so here, this only tells you how many bits it occupies. It's a allocated. So your system ID can be like 0 or 13 or 100 something. And this 8 only means you have 8 binary bits to store the system ID. The actual ID attached to the system is defined in another file.
Okay, makes sense.
Any more questions here?
So, can you emphasize on what does segmentation means here? Because like I know that segmentation is about the size, but like you said something like we can like use it as a spatial resolution. So is it here where we define it? So if I change this grid size in X and Y, this means that I say that, for example, the spatial resolution is like this. Or it is really about the detector geometry itself?
Good question. So, okay, so let's still use this vertex barrel as an example. So this is a silicon pixels sensor.
Mm.
And here 20 by 20 micron is our pixel sensor size. So how we use the segmentation in this particular case is that so imagine that you have this 2D grids created on any of your detector surface. And if you have hit on one of your sensor, and this segmentation basically gives you the ID of which sensor is hit. And later, of course, you can translate this into your actual spatial resolution. For example, if you assume a uniform distribution of the hits across all your sensors, that brings in a factor of square root of 12 in your actual resolution calculation. And if you look at some of the other detector settings, for example, you may see them instead of a squared segmentation, they will have a strip. And sometimes you will see they build in the resolutions as like pre-calculated in their detector design. And this is also this also depends on how you use this information later in your digitization step, which we will go through later.
Okay. So it's really the physical description of our detector.
Yeah, you can think we are using this to mimic the actual detector, some of the actual detector features or layout.
Mm. Okay. Thanks.
Do we have more questions? All right, if not, let's move back to this Jupyter Notebook. And finally, we can start to play with the root files. If you move to the second cell, as I'm showing here, so those are just some of the general standard packages I always like to use, and some configurations of the plots for Python. It's not necessary, just convenient to have. So we will just take hopefully a few seconds, 3 seconds to run this cell. And once all those modules, especially uproot, are loaded, we can move to our first exercise of today, which is accessing the simulation campaign file with uproot. All right, before I have already gave you some code here, so if you like, you can just click this triangle button to run it. And this, oops, I'm sorry about this. This is a stupid mistake. In Python, you always need to pay attention on the indent. Okay, here you go. What I just showed you here is actually under our, so in our remote xroot D server where you have all the simulation files. And I provide the code of path or directory I wanted to inspect. And if you read this path, you can see that we are accessing the reconstructed output, and 24.12 means it's 2024 and December. This is when it's generated. And the detector configuration is Epic Crater Lake, which is our current version. And then I'm accessing event samples from the single particle simulation. And this is actually a single electron at 10 GeV, and it covers the angle of 130 to 177 in terms of theta. And with all those information, the xroot D plugin is able to access this remote directory and give me a list of all the root files under this directory. So in this case, there are 310 in total. And you may want to know how you can find your how you want to find the simulation root files that you are interested in. So, and that is possible if we go back to this page. And under exercise 1.1, I give you a link to this simulation campaign webpage. If we just, okay, so I will need to remember to go back later. Sorry. I should always remember to open a new window. Here we go. Try again, open new tab. Here we go. Campaign datasets. And you can see the format that we went through earlier. We are with December produced of last year. And here, available datasets. You can see there are so many configurations, background, DIS, exclusive channels, status. And if you go to this campaign history, so in theory, they will have a portion of the DD4HAP simulation outputs saved in addition to the final reconstructed outputs. Just in practice, just to save volume, save space. And also because the simulation is not likely to change very often, we have a larger collection of root files available through those reconstructions. For example, if I click on what was done last month, so on the top, it gives you the server address and the part of the directory path. And then you will be able to just assemble your file path step by step. For example, you've add in Epic-Crater Lake, and if you want to DIS, you add DIS/church current /10 by 100/minimal Q square of 100. So you just basically need to go down those layers by layer to go to your final destination. And now let's go back to our Jupyter Notebook page. In this example, we are looking at all those single particle simulations. And then you can just open one of those in the next cell. Let me just hide this, it's a little bit too much, okay. Now it's clean. You can see here, creating the full path of this file, one of those single electron simulation file. And under this simulation file, you actually have at least two root trees. One is events, where you have all those event-based information such as particles and hits, detector hits stored. You also have another tree called the PODIL metadata, which stored some of the useful information we used to create this simulation file. I will come back to this metadata later in this tutorial. For now, you can just open the events tree. Let me just run this cell. Okay, it takes a few minutes, a few seconds. You can see here, it opens the root file and you have about 3,000 events in total. All right, so this is part of our exercise 1. If you go back to our tutorial page. Oh, I should also mention that if you are running the EIC shell, which is a container for EPIC simulation, you will be able to use this standalone xrootd command in command line to access those remote files and download them. You can check the previous tutorials for details. And for now, we have this simulation file open. In particular, we have this events root tree opened. So the next thing we want to do is just inspect the root files. For example, you can use this command to pull out all the branches under this root tree. So now I will just copy this command to a new cell here. All right, and that gives you, let me scroll down a little bit. You can see those are all the informations, and be careful that this is not directly from DD4HAP simulation. This is from actually the reconstruction. So you will see a lot of information. For example, this one is generated through the reconstruction that we will cover later. But otherwise, for example, previously I convinced you that the vertex barrel simulated hits will be stored at a vertex barrel hits as defined in the readout module. So let's see if we have such yes, we do have such a branch under this event tree, which means we have everything consistent. And now if we go back to our tutorial, the next step is once you decided what branch you're interested in, you can extract that branch and convert it into pandas data frame. Of course, you can work with other format. For example, AK here stands for awkward array. Pandas format, the data frame is just my preferred choice because I think it's very easy to display the content, which you will see in a minute. Okay, here, let me open a new cell. You can always create a new cell by click this plus code. And okay, and instead of MC particles, which we will talk about in a minute, let's first take a look at this simulated heads from our DD4HAP simulation. So here you can see that I extracted this branch from the tree and I converted it into the data frame. And okay, let me just get rid of this print. Actually, if you just type this data frame or variable names, you can see that the Jupyter Notebook can render this output very nicely in this spreadsheet. As you can see here, you have entry and sub-entry. So entry here is equivalent to your event ID. So what you see here is that for event, the first event with index 0, you got 3 hits from your vertex barrels. And the cell IDs, if you remember still, are those 64 bits number, which contains your segmentation information. It's saved in binary format, and so you're reading those in decimal. That's why it probably does not make a lot of sense here. And then you have, if we just go through this row, you have the energy deposit, and you have the time of the hit. And then if we go to the left, go to the right a little bit, you have the hit position in terms of X, Y, and Z. All right, so those are the main informations you can see from the simulated hits directly from DD4HAP. And another part of the DD4HAP output is this, what we call MC particles. And this is very straightforward from the name that it contains all your simulated particle information. So depends on how you provided your generated particles. The MC particles will contain, for example, in our case, because we used the particle gun to generate only the outgoing particles. So you will only see all the outgoing particles and their secondaries under the MC particles. If you use, for example, the HAPMC format file, which is generated by Pythia, you will see their parent particles here as well. But go back to this table, event 0, you have a lot hits here. And how you distinguish those hits from your primary particle versus secondary, and is you can look at this generator status. Generator status 1, I think that means it's a primary particle. And also you can see it provides your the PDG ID of a given particle. 11 is the PDG ID for electron. So this, and you can also check the charge here. So this is how you know this your primary particles from all those various secondaries and other particles. And if I scroll, is there a question?
Yes, Karthik here. So what does the simulator status mean here?
The generator status, a
Oh, the
simulated.
simulator.
Okay, so I'm actually not familiar with this. If you really want to know all those definitions, what you need to do is to look back into the data model.
And I was not
So
able to
let
read
me, I will come back
what-
to this topic when we talk, when we discuss data models. I will show you how to look up all those informations.
Okay.
Sorry, I don't have a exact answer for now. All right, so if I go to the right, you can see it records the vertex position, and if it's a primary particle generated at 0, 0, 0, you will also be able to check it here. And all the way down, you see the momentum information of the particle at vertex. It's X, Y, and Z component. All right, I think those are the important informations here. Another question?
I just noticed that there is minus signs for the momentum and this stuff, is it like it's the vector value, right?
XYZ, yes, it's a vector value, and you will need to have a little bit of intuition on the coordinate system. Yeah, sorry. Okay, so actually probably it makes sense for us to look again at the epic geometry. So just wanted to make sure everybody is on the same page. So this is the epic geometry description that I showed you earlier. And let's just look at the inner detector in 3D. So it takes a minute to load the viewer. That's why I wanted to only show you the inner detector part. If you play with this offline, probably you can find a better color here. Somehow it's all grayed out here, but basically you can see all those detector parts, and if you move your cursor to different places, it will show you the name of this detector parts. This is a beam pipe, and for example, this is your top layer, and this is your vertex barrel layer. I think somewhere here it allows me to show XY center. Cool. Okay, so this will give you an idea of this XYZ coordinates of our epic detector system, at least in simulation. You can see that along the beamline is our Z-axis. And vertically up is our Y-axis. And the x-axis goes horizontally and pointing into the paper. Is this helpful? Okay, I didn't see further questions. So let's go back to our tutorial. I do want to pause here for a moment to make sure everybody is able to run the first two exercises and inspect and generate a data frame of the MC particle branch. So please let me know if it's not the case. Okay, I didn't see any questions, so I would assume everybody is able to run the Jupyter Notebook until this step. And then we can do some very simple analysis based on the root file we just opened. So the exercise 3 is you can extract the momentum distributions of the primary electrons. So I just walked you through how we select the primary electrons. For example, you can use one of the conditions, which is a PDG ID. And here is where I can show you this very nice package from the PDG group. Okay, let me open a new cell here. I imported this function called particle from this PDG package, and that allows me to search this particle from the name and it returns. In our case, it is a PDG ID of election. It's 11, as we know, and you can also so once you were able to locate the particle with its name, you can also have the mass and the charge other information. Let's try if we do part dot charge, for example. You can see this is the charge of the electron, and we can also do mass. So see, basically it's a very convenient way, especially when you need to deal with a slightly more complicated root files. Instead of having your own lookup table or hard-coded numbers for each of your the particles you're interested in, you can just call this package. And then I would just need you to copy this part of the code to your own Jupyter Notebook and run it. So you can see basically we have the PDG ID cut and we have the primary particle cut. And with that, you can plot the momentum distribution of all electrons and only the primary electrons. Okay, so I will give you probably 5 minutes for this exercise. And meanwhile, if you have questions, feel free to ask right now. All right. I hope everybody here is able to run the code and get some histogram, just like this one. If you're not really familiar with the Python pyplot package, what I did here is I plot the momentum distribution with predefined bins. And this alpha option here makes my histogram in blue here a little bit transparent, so you can see better when you have when you overlay it with other plots. And then the second part of the code, I applied a cut on by requiring it's both electrons and the primary particles. And that allows me to plot the distribution with the step style. That's why you see this red line surround this peak at 10 GeV. So if you remember previously, when we select the root file, we are looking at the electron at 10 GeV. So this is just what it's supposed to be. Okay, if no more questions, we will move to the next part of our tutorial. Okay, we are halfway through. So the next part, we will be switching from DD4HEP simulation to our reconstruction workflow. So in this section, I will discuss heat digitization, the data model, and of course, the reconstruction algorithms. So very similar to what happened to our DD full HAP detector geometry description, our reconstruction framework, which is called EIC-RECON, you can find its source code on GitHub. The EIC-RECON now will take the simulated hits from all the detectors, and it go through digitization, go through the reconstruction of, for example, tracking, vertex, PID, all those informations, and eventually it provided you the reconstructed particles. And also some of the physics observables. Okay, here I'm showing you the GitHub page for the EIC-RECON package. If you scroll down, you will find the documentation website, and also if you want to do reconstruction on your local EIC shell container, you can follow those steps to compile and configure your environment. Okay, for today, so there are so many subsystems that EIC-RECON takes care of. Today, I will just use the tracking system as an example. So previously, I also already showed you how where to look for the raw tracker hits. Now I will just move to the further step down to the workflow and show you how the tracker hits are digitized and reconstructed into trajectories. If you are interested in other detector system, I would encourage you to check those presentations from the EPIC collaboration meeting in July last year at Lehigh University. This is, as of now, I know for now, still the best reference. Actually, so let's just take one moment to look at this web page. So from each of those presentations, you can see by name that people give you a very brief introduction of the workflow of each system. For example, if you are interested in tracking, in our case, you will see this flowchart, how we get the tracking information from MC particles, going through simulation, and going through reconstruction algorithms, which I will discuss later. Okay, let's go back. There are many reconstruction algorithms in EIC-RECON, and each of those algorithms, or let's say it's a small module or step, it contains 3 key components. So I'm not going to discuss all those infrastructure today, but the 3 key components you will be aware of when you just look at the EIC-RECON package yourself. Is this algorithm itself, which is often a .cc file. And then there is something called, this is a JOmni factory. Often it's named as, for example, tracking trajectory _ factory, something like that. And that is a place you can find the algorithm and the data type declaration. And also, you will have one piece of the code that actually generates the factory and the algorithm as described in those 2 parts. Let's take digitization as an example. So all the detector heads go through this digitization step. And that is done like separately for each subsystem. In our case, we will just look at the vertex barrel hits. And the algorithm we used to handle this digitization is called the Silicon Tracker Digi. And I will, because this is not a tutorial that I wanted to teach you how to become a developer for ES-RECON. I mean, if eventually you are interested in contribute to the actual algorithms, that would be nice. But here I'm trying to think a little bit in the opposite way, which is if you are a user and you see something like one branch is either, for example, tracking trajectories, or you see your vertex hits or MPD hits or some detector hits, and you want to know how your detector information is processed through this reconstruction workflow. And so this is probably the first step you will start your search within ES-RECON, is to look at this factory generator. How to get there? If you know your input or output, my suggestion, at least for this tutorial session, would be you just use the search function provided by the GitHub. If you have, for example, VS Code or other IDE set up, you can also use that for easier navigation. But here, for example, I'm just showing you if you want to know, for example, how our simulated vertex barrelheads are processed in simulation digitization, you can simply use this search window. Again, this is just for demonstration. You may have a better way to handle it offline. Sorry. I definitely made a mistake here. Let me see. Sorry, I need to move this Zoom window a little bit so it's not blocking my view. Okay, search or jump. Within the repository ES-RECON, let's just search the keyword, and let's go to the code. Okay, sorry. So because this is a private window, I will need to log in. So Stephen, if you can pause a minute. Okay, now you can see that GitHub gave you all the files contain the character string vertex barrelheads. And luckily, the first file here is actually where you generate the hits. Okay, if you click on this block of the code, it's a digitization. You can see that it calls a factory called the Silicon Tracker Digi. And this is just the name of this factory module, or if you want to call it application, that's fine. And then you have the input, which is vertex barrelheads from our DD4F simulation, and it produced two output, which are the vertex raw hits and also the vertex raw hit association. I will explain those two later. And if there are any configuration you provided with your algorithm, you can also put it hard-coded here. You can also provide those information by using the comment line flag. So in this case, I would say this format or something like a block of code looks like this is really where you want to start your search, because it clearly tells you which algorithm it used, and it tells you about the input and outputs of this algorithm. All right. And you may want to know later, like how exactly this this digitization is processed. So that means we need to go into the actual algorithm to take a look. But before that, we actually want to take a look at this factory. Silicon Tracker Digi _ factory. if you remember earlier, I mentioned the factory as a place where you have your algorithm defined and also your input and output. As you can see here, PODL input is your simulated heads. And in this bracket is actually your data type of the input. And here you have two output and their data types. And you also have the configuration options defined here. So that gives you a little bit more information. So now you not only you know the name of the input and output branches, you also know their data types. And why data types matters? Because how our EIC Recon or the entire EPIC simulation package is configured is that if you want to save any of this information into your final root file, it has to be stored in some predefined data model. And you can see here, you see two types of data model, EDM4HAP. This is more general data model that we inherited from the standard high energy particle physics simulation packages. In this case, you can see all our simulation heads are handled in this EDM4HAP format. You want to know more about the format, probably the best thing to do is just to copy this and Google. And similar thing happened actually to the MC particles. One of the earlier question was one of the entries in the simulation MC particles field. If you want to know that, because that is another EDM4HAP object. Actually, let's do, sorry, so it's probably M4HAP, MC particles. Okay, great. And the GitHub immediately bring you to this data model page. And data model page for EDM4HAP, you can see all those different definitions of the data model. You start with vectors, covariance matrix, and if we just search MC particles here we go, MC particle. And each of those fields are defined as members here. And you can finally find some information on the simulator status. I hope this is helpful. Because it seems it's in bit constant, and you will need to really look into the documentations to understand what those numbers mean.
Right. So my experience, though, the reason I asked for that is, at least within the EPIC case, these things are not set, like the one below, like set created in simulation, so on and so forth.
Okay.
That is not set, or like I'm not able to call those functions off. So that's why I kind of asked if there was any difference between EDM for EIC and EDM for HEP.
Okay. So in terms of the MC particle, they should be consistent. Because this field, I think MC particle, the entire branch is just filled by the DD4HAP. I don't think we did any alternation of that. All right, so and then let's just go back to our tutorial. So we went through this factory generator, and we also went through this factory declaration itself. And I just showed you how to locate one of those data model for your input. And now let's look at the EDM4EIC, which is what our software group created to handle specific type of data within the EPIC simulation. And of course, there should be a link. Here you go. Okay, so this link directly bring you to the EDM for EIC definition. And let's remind ourselves what data type we are looking at. Okay, let's look at the raw tracker hit. I will just search raw tracker hit here. And you can see that the digitization algorithms, it takes your simulated hits as input, and as output, it only actually keeps or stored 3 fields, which are the cell ID, the charge, and timestamp. Which means that in our later stage of the simulation, we will not use other informations, for example, the real position XYZ from the simulated hits. Instead, we only have this cell ID. And if you have hits that happen to go through the same cell, the same segmentation cell as we defined earlier, it will have the same cell ID. And that is exactly how digitization is supposed to work when you try to when you try to simulate the behavior of our actual detector system. All right. And then I think we are ready for some exercise here. Well, almost ready. So one more thing to mention is that as a other output from our digitization algorithm is something called the tracker hit association. Association is a special type of object that we created to store the relation, as you can see here, between the raw hits, between the simulated hits and digitized hits. That allows you to, like when you look at the simulated hits, you can follow these relations and go back and see what are the what is the corresponding simulated hits. So this is defined as a 1-to-1 relation. So it's always 1-to-1 mapped. And if you look at the actual digitization code, you can see how we filled those associations here. Basically, we have the cell ID, basically we have the weight, and this is actually a pointer to your digitized hit. And this is your associated hit from the simulation. Okay, let me see. Okay, before we go into the next exercise, just wanted to mention a little bit. So so EDM for HEP are what we basically just use as a standard part of the data model. But EDM for EIC is what we created to best serve the interest of our simulations and physics analysis. That means if in the future you think there are certain informations that you wanted to look at, but you didn't see it in the current data model, you can just make a request to the software and computing group to add that field. And also, if you in the future wanted to design your own tracking algorithm, and you find that all those existing data model cannot host all those informations you want to store in your output, you can just request to create a new data model under EDM for EIC. This is so this file, as you can see, is part of the EIC software project. So once you become a developer, you will have access to and the permission to do pull request, for example. All right. With that, let's go back to our next exercise. Here, I will ask you to do a little bit of search within the EIC Recon GitHub repo and find a list of other detector systems that use our silicon tracker DJ algorithm for digitization. I think I will give you 5 minutes for this. Basically, you just need to if it was me, I would just go to the EIC Recon repository and search the keyword here. But you have feel free to do whatever work best for you. Yeah, we will continue in 5 minutes. And meanwhile, if you have any other questions, feel free to ask. Okay, I hope everybody have a little bit of time to explore. And now I will just do what I described. So in order to see what are the other detector systems or output generated by our silicon tracker DJ algorithm, I will just do a search here. And you can see the algorithm header file itself, the factory itself. And if you scroll down a little bit more, here you go. You started to look at files from under detectors, Raman pods. This is our barrel vertex tracker, low Q-square tagger, and barrel TOF, B0 tracker, I think this is probably the silicon barrel tracker. Aha, yes, by this name, its name, and also MPGD and Kaptov. Okay, so you do have a very long list of different detector parts using the same digitization algorithm. I wanted to know that how many of you were able to extract those information? Or how many of you had issues here? Okay, if not, I will stay here for one more second for questions, if any. Okay. If not, let's continue. Finally, we can talk about track reconstructions. This is instead of me just to talk a little more, I think this is more an exercise for everyone. So previously I used the digitization algorithm as an example and showed you how to go through the three key components of the reconstruction algorithm. And now I would ask you to do the similar thing to find what we use for track fitting and reconstruction. In this case, it's called the combinatorial common filter. And this is itself, CKF itself is an algorithm provided by the ACTS library. And we call this function and assemble the input and output in the code called a factory called CKF tracking. Okay, so this will be a slightly longer exercise. I would ask you to first locate the CKF factory and the input output. And then I would ask you to find where the CKF tracking factory is generated. If you remember, you will be looking for a block of code like this. But for CKF factory, CKF tracking factory instead of silicon tracker digit factory. And starting from that, you will be able to navigate to upstream and downstream variables. And eventually you will be able to draw a flowchart from the central tracker measurements all the way through the CKF tracking to the central tracker vertices. Okay, so two steps. First, to find the CKF algorithm, and the next step is to find all its upstream and downstream input output from the track measurement to vertices. This is I will stay here for probably 8 minutes, and meanwhile, yeah, so I will give you like 4 minutes for the first step, and feel free to ask questions. So Stephen, so I just wanted to quickly check, did you see questions from Mattermost or other places?
I haven't checked the Mattermost, but I've been monitoring the chat. I'll see if there's anything in the Mattermost quickly as well.
Okay, thank you. Okay, now let's just look at the first part of the exercise together, which is find the inputs and outputs for the CCAP tracking factory. That I will go to the EIC Recon search window again, and just to type CCAP tracking here. And that brings me to the actual algorithm.cc, the factory. And if I scroll down all the way, here you go. So under tracking.cc is where the CCAP factory is generated. Let's go to this code. Okay, there are a lot of useful information in this piece of the code called tracking.cc. First, you can see that here are collections of all the tracker hits that we wanted to include in our, we wanted to use in our tracking algorithms. You can see it's from different sub-detector systems. And then if we scroll down a little bit, you can see step by step that we have all the tracker hits are combined into a big big collection called the central tracking reconstructed hits. And from there, the next factory takes the reconstructed heads as input and convert it into central tracker measurements. And this is the starting point for the second part of our exercise. But now let's just move down. You can see that finally we're looking at the CCAP tracking factory. It takes the initial check parameters from MC particles, as well as all those tracker measurements as input. And as output, it provided you ACTS format trajectories, as well as tracks. So this particular collection, you can see from the name that it's actually not a standard data model in EIC Recon, because it's actually something defined in ACTS, the tracking library we're using, and it will not be stored in the final reconstruction output either. What we did here is we used another algorithm, ACTS2 tracks, to convert those non-standard output collections into some data model that we defined in EIC Recon. No, sorry, we defined in EDM for EIC. And those are the things that you can safely store in your reconstruction output. And if we move down to this algorithm, you will see that we have trajectories and tracks. Trajectories and the tracks go through something called ambiguity solver. That's where you can sort out if there are overlapped tracks, or if there are two tracks reconstructed from the same initial particles, something like that. And eventually you have all those seeded, you have those tracks filtered. And if I keep scroll down, you will see that the CCAP tracking factory is called again, because the CCAP tracking, this itself is just an algorithm. You can use it many times just to give it a different name, and If you want, you can use the same algorithm, just as what we did previously in digitization. You can use the same algorithm to handle different groups of input and output. In this case, the difference is if you pay enough attention in this name here, you have seeding. And excuse me, previously, everything you saw comes with the name of choose-seeded. So the difference is if you provide the initial guess to your Kalman filter algorithms through the choose information, which is MC particles. If I scroll up a little bit, you will see this initial check parameters. Those are choose information for MC particles. In other words, in real life, you do not have access to those choose information. And in another case, we actually have an additional step of seed finder. Basically, you start from all the possible combination of hits. You're trying to find the triplet that can potentially extend into a good trajectory and use that as initial guess to your Kalman filter. And this is what happened in your central CKF trajectories factory. And then if you scroll down, you have all those trajectories. And finally, you see something called the iterative vertex finder. This is the algorithm we use right now to do the find the primary vertex. And you can see that it takes trajectories as input, and it gives you the vertices as output. All right, I hope now you were able to follow me and see how we process those detector information step by step until we reach a point that we were able to reconstruct the trajectory and find the vertex of the particle. Are there any questions so far? Okay, if not, let's move to the next and the final part of our tutorial today. I think we're still doing okay in terms of time. Nowadays, I walked you through how we process the detector information and go through a few reconstruction algorithms. And it's time to finally take a look at the reconstruction output file itself. So again, we have two root trees. One is the event tree, which you can find the MC particles and many detectors simulated hits collections. Those are directly copied from the DT4HAB simulation output. And then you will have you could find many output collections which are generated by different steps of the reconstruction algorithms. And again, if you want to save them, they should be either EDM4 HAB or EDM4 EIC object. So you probably do not want to save, or in practice, we do not want to save all the intermediate product of the algorithms. There is a default list of the collections that we save in output, which is located in this file. And let's just take a look. Okay, go to File. So here is how we process the event. And if you scroll down a little bit, you can see here you have output collections defined. where you have all information about the MC particles and the hits, trajectories, and hits from different detectors. All those informations, if you scroll down from the detector hits all the way to reconstructed particles. And also there are different algorithms that process part of the reconstructed information and give you physics observables. All the output collections are defined under this JEvent processor pod.io.cc file. So you know that what are the output that you can expect from your final reconstruction output root files. You can also customize the output collections by using the command line option if you choose to run EIC recon in your local containers, which you can look at the documentations for more details. And now a little bit more words on some special members of the data structures. So previously you have seen an example of relation, which is our association between the simulated heads and the digitized heads. And the other example of the special vector member, if we just look at the central CKF trajectory collection, so all the special members like vectors or relations, their branch name or collection name started with this underscore. So first, let's just see what are the special branches or members we have, for example, for this CKF trajectory. Okay, so let me just create a new cell here. And this allows you to pull out all the special members under the CKF trajectory. You can see there are track parameters, measurements, and the measurement chi-square. So you will not be able to tell just from the name here, which are the relation, which is essentially a pointer, and which are the vector members, which is by name of vector of values. What you could do, for example, is you can look at the corresponding data model as defined in EDM for EIC. Let's see if we still have this here. Okay, so if we go back to our EDM for EIC file, and so in this case, I know I'm looking at the trajectories. If you are not sure about what exactly is the data model you use to host your output collections, you can again go to the algorithm factory to check. And here you can see clearly that under the trajectory, you have two vector members which record the chi-square of each of your measurement heads or outlier heads. And you also have the relation that associate your trajectory to the corresponding track parameters and the list of measurements. And if you used a seed to start your CKF track finding. Okay, now it's clear, and let's talk about how to access those special members. So first, let's look at the measurement chi-square, which is a vector member. What we can do is exactly as before, we know the name of the collection. Even it's a little bit weird to start with underscore, you know the name. And you can just extract this branch from your root tree. Okay, so this is a vector member. That's why for each event, what you have is just a list of numbers. And let me see actually if I can just isolate the so here it shows you all the measurement chi-square in our case associated with the first event. In this particular case, it's very simple because we are dealing with a single track, single election, which means one event you only have one trajectory. So you immediately know that those are the list of measurement that my chi-square of measurement belongs to this trajectory. But in some cases, when you have multiple trajectories, this vector member will still just store everything from multiple trajectories into one big vector. And that case, you will need to know the starting index of a given trajectory you're interested in. And how you can do that is if you go back to the main collection, which is the CCAF trajectories. Okay, and you can see here if you go to the right, there is one column called CCAF trajectory measurement chi-square underscore begin. That basically tells you the index that so where your so in this case, this is event number 0 and the trajectory number 0. And this quantity tells you within the big vector of measurement chi-square, which is this one, where your measurement chi-square values starts for this corresponding trajectory. All right. And again, in your case, you have only one trajectory. That's why you see it ends at 7, which is basically takes all the members from these vectors. All right, so this is how you deal with vector members. And the last thing you wanted to see here is probably how you deal with the relation. So that will require us to look at the other root tree we have not talked a lot about earlier in this tutorial, which is called the PODA metadata. PODA metadata, again, it contains a lot of useful information. Actually, we can, let's see. Let's first pull out this root tree for metadata. I do not want to mess up with my previous work, so I will just create another cell. Well, for a good practice, actually, it's probably better if we just add a section here. So Jupyter Notebook, it takes text, or you can just use Markdown format. There you go, and it automatically created a section or subsection in this case. Of course, we want a section. Okay, great. And here I'm going to work with just the metadata. The first thing is I wanted to switch to the correct tree name. Let's call it the tree meta. All right, so you can see that under the PODA metadata tree, we have 4 branches. And if you still remember, we can use the same command to list all members of this tree. We don't need a filter in this case, you just put a star. There are 4 branches. Today we're interested in this events ID table. So the next step will be just to do what we did earlier, extract this branch and convert it into a very nice data frame table. Okay, cool. Now you can see that it is a table that you have all those names corresponding to each of those output collections. MC particles, different detector hits, associations, PIDs, all those informations. Each of those collections, they have a unique collection ID. And you will need this relation to retrieve your relation members of certain branch. And let's go back to the example earlier with the trajectories. One of the members of the trajectory is this track parameters. But in our case, it's always 1-to-1, so it's not a super good example. So let's take a look at this measurements. It's so we are like in the future it will be deprecated as indicated in the name and reintegrated into a different collection. But for now, I think it's still good for just illustration purpose. So this trajectory measurement, so actually let's look at this trajectory measurements. It gives you a list of pointers that allow you to trace back to like so what are the actual detector hits are used to fit this trajectory, which is very useful information if you want to check your tracking performance and understand how your tracking algorithm actually work. Okay, in this case, if we just let's just reuse one of our earlier cell, and here we wanted to show all those measurement members. Okay, actually now you can see that it has two columns. The first column gives you just an index, and the second column gives you collection ID. So the collection ID is the information you can obtain from your metadata table. Sorry, I have to scroll up and down many times. So here we know this is our collection ID, and we can just do a cat here. Here you go. And that point you back to this central checker measurement collection, which makes a lot of sense because we know central checker measurement is exactly the input to the CKF tracking code, CKF tracking algorithm. Okay, and then what's next would be if I go back here. So again, so there is a collection ID and there is an index. And what it says here is actually, if you look at the 7th, or like starting from 0, this is 8th member of your measurement hits. This is, you will find the first measurement of the actual trajectory. It's a little bit convoluted here, but the idea is that from the trajectory, you know that this trajectory have like 7 hits, 7 measurement, and you want to see what exactly is the measurement or tracker hits used. So the first one in your trajectory hits is index 7 tracker hits in your measurement collections. And that allows you to go one step back and to find the actual measurement hit. And you need to go actually one more step to find the actual detector heads, because if you remember, measurement is a big collection of all the detector heads. That is something I can show you here. Okay, saying that, we look at the central checker measurement here. So all those measurements, those are 2D space point attached to some detector surface. And you will need to, for example, here, go one more step. You have this hits as association, I believe. Oops, that's wrong. Go, okay, so give me one moment. Okay, underscore hits. Yeah, here we go. So that is another relation member of the under the checker measurements. So you can see exactly which measurement hit comes from which detector hit collection. And for example, in this case, if we just search by this collection ID, actually, let me hide this part. Okay. Okay, so you can see that the first measurement hit we looked at is from this checker hits collection. So basically, this is with this association, or sorry, with this relation member, you can go back step by step to see how those information are used to generate some quantities that you are interested in. So in our case, I just show you an example of how we trace back the checker heads from the trajectory, reconstructed trajectory. But it can also be like what are the trajectories goes into a vertex finder. And it can also be what are the trajectories go or PID information goes into your final reconstructed particles. So with all those relation members, you can go step by step. Of course, this part is a little bit more involving that requires you to do some coding and to sort out basically the workflow step by step. But if you just are dealing with some physics analysis and you wanted to make sure that your observables are generated correctly, which means you want to make sure that it takes the correct information and the algorithm itself works. You will need to, hopefully those information, what I showed today will help you navigate backwards through this EIC-Recon repository and either to do troubleshoot or just to in general know more about the algorithm. With that, I think we come to the end of this tutorial just in time. So for the future, if you are interested in learning more, you can look at different tutorials, which will tell you how to run your own simulation and reconstruction, and how to develop your own reconstruction algorithms. And if you are more into the analysis, how you can develop some of those analysis benchmarks based on the reconstruction outputs. That's all for today. And again, if you have more questions, feel free to ask.
Yeah, thank you very much. Yeah, there's time for a little bit of if anyone has any questions. If not, as well, just as a reminder, this once the recording is available, I'll get it uploaded with some creative editing, and after that, it'll go on the YouTube page at some point as well. But I'll post in the tutorials channel on the Mattermost the link as soon as it's available.